Now that we've seen the set of registers available in an ARM processor, let's look at how we actually command the processor to use them. This page introduces the basic structure, or syntax, of ARM assembly language. We can group the instructions into three fundamental categories. First, we have data processing instructions. Think of these as the calculator functions of the processor. They perform arithmetic and logical operations like addition, subtraction, or moving values. The general format is operation, condition, RD, RM, op2. Let's break that down. Operation is the command, like ADD for addition or SUB for subtraction. Condition is a very powerful feature of ARM. It allows an instruction to execute only if certain conditions are met, like if the result of a previous operation was 0. RD is the destination register, where the result is stored. And RM and op2 are the source operands, the values we're working with. Look at the first example. ADDEC R4, R5, R6. This means if the equal flag is set, then add the value in register R5 to the value in register R6 and store the final result in register R4. The next one, SUB-R5, R7, hashtag 4 is a subtraction. It takes the value in R7, subtracts the immediate value 4, the hashtag symbol tells us it's a number, not a register, and puts the result in R5. Second, we have memory access instructions. These are crucial for moving data between the processor's fast internal registers and the main system memory. LDR stands for load register, and STR stands for store register. The example LDR R0, R6, number 4, tells the processor to go to the memory address calculated by taking the value in R6 and adding 4 to it, and then load the data from that memory location into register R0. SDRB is similar, but it stores data. The B in SDRB means it's storing just a single byte. There's also a very efficient version for moving blocks of data, load and store multiple instructions like LDMIA and SDMFD. The example SDMFD SP, bar4, R11, LR is a very common instruction you'll see at the start of a function. It means store multiple registers. It takes a range of registers, R4 through R11, plus the link register LR, and saves them all to the stack. The SP is the stack pointer, and the means the stack pointer register is updated automatically after the operation. Finally, we have program flow instructions. These instructions control the execution path of the program. They are what allow us to create loops and call functions. B is a simple branch, which is like an unconditional go-to. B bar simply tells the processor to jump to the code label named bar and continue from there. BL is branch with link. This is how you call a subroutine or function. When BL foo is executed, the processor stores the return address in the link register, LR, which we saw on the previous page, and then jumps to the foo label. When the foo function is finished, it can use the address in LR to return to where it left off. These three instruction types are the building blocks for any program you write in ARM assembly. When we use BL to call functions, there's a standard convention for how to pass data in registers, and we'll dive into those rules next. When you write a program, especially in a language like C, it's often broken down into many small functions. When one function calls another, they need a clear set of rules for communication. How do you pass information or arguments to the function? How does it give you a result back? This is where the AAPCS comes in. AAPCS stands for the ARM Architecture Procedure Call Standard. Think of it as a contract or a set of conventions that compilers and programmers agree to follow. It ensures that code compiled separately, or even code written in different languages like C and assembly, can call each other without problems. The AAPCS is a fundamental part of the larger Application Binary Interface, or ABI, for ARM. The core of this standard is about how registers are used during a function call. The page categorizes them based on their roles. First, we have registers R0 through R3. These are the primary couriers for function calls. They're used to pass the first 4 arguments into a function. For example, if you have a function calculate A, B, C, A would go into R0, B into R1, and C into R2. These same registers, particularly R0, are also used to return a result from the function. The slide notes they are otherwise corruptible. This is a key concept. It means that the function being called, the callee, is free to change the values in these registers. If the calling function, the caller, needs the original values that were in R0 to R3 after the call, it's the caller's responsibility to save them first. What if your function needs more than 4 arguments? Any additional parameters are passed on the stack. Next are the register variables, which are registers R4 through R11. The rule for these is the exact opposite. They must be preserved. This means if a function you call wants to use register R7 for its own calculations, it has a responsibility. It must first save the original value of R7, usually by pushing it onto the stack, do its work, and then restore the original value before it returns. Because the callee does the saving, these are often called callee-saved registers. This allows the caller to place important variables in these registers and trust that their values will be unchanged after calling another function. Then there's R12, the scratch register. As the name implies, it's a temporary register that can be used for short-term calculations without needing to be saved by either the caller or the callee. It's a handy, disposable register. We've already seen R13, R14, and R15, the stack pointer, SP, link register, LR, and program counter, PC. In the context of function calls, the link register R14 is especially important because it holds the return address. A common practice, as noted at the bottom, is for a function to immediately save the LR to the stack. This not only preserves the return address, but also frees up R14 to be used as another temporary register. A couple of other crucial points from the slide. The CPSR flags, which we use for conditional execution, may be corrupted by a function call. A function might perform calculations that change the flags, so the caller can't rely on them remaining the same after a function returns. And notice the note about the stack pointer. It should always be 8-byte aligned. This ensures maximum performance for instructions that load or store multiple values from memory. Ultimately, if you're ever writing assembly code that needs to interface with C code, you must obey these AAPCS rules. This standard is what makes modular programming and software libraries possible on the ARM platform.